Good morning, students. Um, we are going to discuss. In Neet 12th standard, that atoms lesson. Please hold on just a minute. Okay, it's not clear. Wait. Okay, I hope it is somebody. Yes. Just a second. Okay, students. Today we are going to discuss the Neet part, physics, atoms lesson. Okay, so I observed the most of the questions asking from the hydrogen spectrum line and ratio oriented questions, and then velocity of the electrons related questions, then relationship between that energy and so let's we discuss the first question. See that the first one, the ratio of kinetic energy to total energy of electron in Bohr's orbit of hydrogen atom is. Good morning, Arshia, Akshaya, and Zeena Priya. Good morning, everyone. So, this is the first question. Is asked in 2018. The ratio of kinetic energy to the total energy of electron. Okay. Actually, this is a very easy question. So, within 10 seconds, you can possible to answer. So, if you know that the direction. That the direction answer. If you know that direct answer, so easily we can say. But anyhow, I will explain that theory part a little bit. So please remember that. See that actually the potential energy and kinetic energy, this is total energy. So please listen. Potential energy kinetic energy, total energy. So please remember that potential energy comparing to the total energy, that is -2, kinetic energy is 1 time, then total energy is -1. So this is the ratio we got from the theory. Okay, but anyhow, simply just you add potential energy -2, kinetic energy 1, so total energy means you must add. So we can get -1. Okay. So now they are asking kinetic energy and total energy ratio, that is 1:-1. Okay. Actually, we can say directly. Okay. Right. So how we know this potential energy -2, kinetic energy 1, then total energy -1? This is from the theory. So just I recapitulate. Okay. So please listen. First, I can write kinetic energy. Okay. So, the kinetic energy, the normal formula, you know, that is half mv squared. So, kinetic energy is equal to half into, you know, this mv squared term, it is from Bohr's atom model. So, we know in that Bohr's atom model, in that electrons having the centrifugal force from the derivation, that centripetal force we can relate it with that electrostatic force between the nucleus and the electron. That is, mv square divided by r is equal to Zt square divided by 4 by epsilon naught into r squared. So this term. Okay. Then the both side in the denominator, r value cancel. So remaining one more r is there. So left side we can get mv squared. So now we know in that kinetic energy mv squared, instead of this mv squared we can write this term, that is Zc square divided by 4 by epsilon naught into r. Then therefore kinetic energy is equal to 2 into 4, we can write 8. So we can get one kinetic energy. This is one kinetic energy equation. Okay, right. See that next step, potential energy. I mentioned in blue color, potential energy. So that potential energy generally, that is U is equal to 1 by 4 by epsilon naught Q1 Q2 divided by R. You studied in electrostatics lesson. The same thing only. Here the potential energy between the nucleus and the electron, that is we can write minus Ze square, minus is represent that electron, so minus Ze square divided by 4 by epsilon naught into R. Okay, right. So now I can comparing with the previous equation. So for that I can multiply and divide by 2 extra. So in the denominator I can get 8 by epsilon naught R. Okay. So in the kinetic energy equation also 8 by epsilon naught, here also 8 by epsilon naught. But in the numerator, here Zt squared, but here minus 2 Zt squared. So now we can comparing this potential energy and then kinetic energy. Okay, right. So if kinetic energy one time means potential energy minus 2 times. So that only difference. Here 1 times of this value, here minus 2 times of same value. So we know that potential energy is equal to minus 2 times of kinetic energy. You should remember that word. Okay, right. So now we know what is the kinetic energy value, what is potential energy value. Now the total energy value. So directly substitute we can get, okay, actually potential energy minus 2 times kinetic energy, so plus kinetic energy, so we can get that is total energy is equal to minus that value. Okay, so kinetic energy is 1 time, potential energy is minus 2 times, so total energy is minus 1 time. Okay, so now this question we are discussing about that hydrogen atom, so Z value taken as 1. So see that now you know this meaning, potential energy minus 2 times, kinetic energy is 1 time, then total energy is minus 1 time. Okay, right. In this question they are asking the ratio of kinetic energy and total energy of hydrogen atom, electrons in the hydrogen atom. So kinetic energy 1 time, total energy minus 1 time. This is the answer. Okay, so maybe relationship between potential energy, kinetic energy, or potential energy, total energy. Okay, in any way it is possible to ask. Okay, right. So I hope you understood this question. Next, let's we go for second question. Okay, listen, dear students, in this atom lesson I observed very easy question only asking, not that much level difficult. Okay, so easy questions only asking, so please listen. Let's see that second question. Listen, second question, the ratio of wavelength of last line of Barber series and last line of Lyman series. Okay, last line of, okay, what asking, that is a wavelength for Barber series, particularly last line. Then the wavelength of Lyman series, particularly for last line. So this ratio is asking. Okay, right. So just you remember that hydrogen spectra, Lyman, Balmer, Paschen, bracket, fund. Okay, so whenever they mention the last line, means that is represent N2. That N2 is now infinite, because that infinite lines are there, energy levels are there. So the last line means that is represent infinite. Please remember. So N1 is represent that particular series. Say for example, Lyman series means N1 is equal to 1. Balmer series means N1 is equal to 2. So please remember. So based on that key points, let's we see that. So first I will give that idea. Okay. So please listen. The spectral lines of hydrogen atom. Spectral line of hydrogen atom. We know the formula. 1 by lambda is equal to R into 1 by N1 squared minus 1 by N2 squared. So now we know N1 is represent that particular spectra. Okay, already I told you, know. So Lyman means 1, Palmer means 2, like that. Then N2 is represent very next level. So commonly we can say N2 is equal to maybe 2, 3, 4, like that, etc. So this is a common formula. So 1 by lambda. So this is that wavelength. So you know that one more idea. 1 by lambda is nothing but that is a wave number. Okay, lambda only we can say wavelength. 1 by lambda is known as that is wavelength. It is represented by mu bar. That is also represent. Remember. Then R means Rydberg constant. That is 1.0994 into 10 power 7 per meter. Okay, right. So now we are going to compare the Balmer and the Lyman. So let's say write for Balmer. So 1 by lambda b. So wavelength for Balmer is equal to R into, so Balmer series, it is a second level. Okay, so N1 become 2. So that is N1 square, that is 2 square minus, they said last line. So N2 is, whenever they said last line means that is infinite only. So 1 divided by infinite square. So anything divided by infinite is 0. So we can write 1 by lambda b is equal to R divided by 4. That only I wrote here. Okay, right. Like that, next one, Lyman series. Lyman series, that is 1 by lambda L. R into Lyman series, that is the first one. So 1 divided by 1 square minus, here also mentioned last line. So infinite square. So anything divided by infinite is 0. So we can get 1 by lambda is equal to R by 1. R by 1. Okay, or R. Okay, right. So now the question is the wavelength of the Balmer series to the wavelength of the Lyman series for last line. So for last line I derived already. So directly I substitute. 1 by lambda b is equal to R by 4. Therefore lambda b is equal to 4 by R. Like that, 1 by lambda L is equal to R. Therefore lambda L is equal to 1 by R. Okay. So here R value cancels. So remaining 4 by 1, that is 4 is there. So if you observe that answer 4:1. So in the question they gave 4. Okay. So please listen. Option B, 4. So 4 is the answer. So that ratio is 4. Okay. So easy question. Okay. These spectral lines of hydrogen atom. So this formula is highly important. So please remember that. Right. So second question is over. Next, third question. Third question, please listen. Given the value of Rydberg constant 10 power 7 per meter, the wavelength of the last line of Barber series in hydrogen spectrum. See that, even comparing with the previous question, it is so easy. Even the same model repeated. Okay, even the previous question they are asking a ratio, but here directly they are asking. Here also the last line. So I hope you found the answer. Okay, so please listen. So within half minute we can find the answer. So please listen. So Rydberg constant value they said is taken as 10 power 7 per meter. Then the wave number asking, that is that is 1 by lambda, the wave number of the last line of the Barber series of hydrogen spectrum. Okay, you know that wave number is nothing but that is mu bar or 1 by lambda. Okay, not lambda. Okay, remember, see that this is 2016 question. Now see this answer. See that I mentioned the same formula only, 1 by r, 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square. Please remember that 1 by lambda is nothing but, I think somewhat brightness. Okay, so 1 by lambda is nothing but that is the mu bar. Okay, so this is wave number I mentioned here. It is a wave number. Okay, it is a wave number. So here in this question the given value, that is the Rydberg constant, is equal to r is equal to, I mentioned wrongly, just a minute, 10 power plus 7. Yes, 10 power plus 7 meter. So please change it. So r is equal to 10 power plus 7 per meter. Okay, here 10 power plus 7. Okay. Right. While I send the notes, I'll recorrect and send. R is equal to 10 power plus 7 per meter. For Barber series, we know n1 value is equal to 2, n2 value, they said last line. So let's take that is the infinite. Okay. After that, so the wave number is equal to r into 1 by 2 square minus 1 by infinite square. So this is the 0. So remaining r divided by 4. So r value that is the 10 power plus 7. So once again I will check with the answer. Option C. Yes, correct only. So option C, 0.25 into 10 power plus 7 per meter. Okay. So here mu bar 10 power plus 7, actually it is plus 7, 10 power plus 7, then 1 by 4. So answer 0.25, because 1 by 4 we can write 0.25 into 10 power plus 7 per meter. So that is given as option C, 10 power plus 7. Okay, 0.25 into 10 power plus 7. Okay, I will send the notes, I will recorrect and send to you. The next one, question number 4. So please remember, in the third question, 1 by lambda is nothing but that is wave number. Okay, right. Next question number 4. Listen, question number 4. When an alpha particle of mass m moving with velocity v bombards on heavy nucleus of charge Ze. So the distance of closest approach from the nucleus depends on mass. Okay, so this question 2016. This is from that alpha scattering experiment. We know the concept that is closest approach distance. So from that asked, so if you know the concept, so now you can say the answer immediately. So it is purely related with, that is a relationship between the closest approach distance, that is r naught and mass, that relation only asking this question. So just once we recapitulate that theory, so please listen. So please listen. So we know that that the distance of closest approach from alpha scattering experiment, we know here the more number of alpha rays is moving towards the nucleus, but we know exactly from the center of the nucleus, so that alpha particle only, it will be returned back, I mean it will be returned back with 180 degree. So you remember this theory. So that distance between that turning point of the alpha particle and then center of the nucleus, you know, that is r naught, that is closest approach distance. So now in this position what happened? Okay, so please listen. So here what happened? So that is a very important point. So we know that here alpha particle moving towards the nucleus with high kinetic energy. Okay, with high kinetic energy. But while we reach at particular distance, here there is a electrostatic repulsive force between this alpha particle and the nucleus, because this is also positive nature, this is also positive nature. So some highly repulsive force is acting in between them. So this entire kinetic energy is converted to that electrostatic potential energy. So please remember that theory, that only I mentioned here. As the alpha particle, as the alpha particle approaches the nucleus, the electrostatic repulsive force, so here you know the electrostatic repulsive force due to the nucleus is increasing. Okay, so here the electrostatic repulsive force is increasing. So what happened? The kinetic energy of alpha particle, so here you know kinetic energy of alpha particle, so that kinetic energy of alpha particle become converted into electrostatic potential energy. So here in this position the kinetic energy of alpha particle is equal to, that is converted potential energy. So you remember the theory, the based on that point we can solve this question. Listen. So now we know based on this diagram concept. Okay, so not clear. Okay, so please listen. So at the distance of closest approach, we know the kinetic energy is equal to potential energy. So kinetic energy of the alpha particle, you know, that is half mv squared is equal to potential energy, you know, that is k into q divided by r naught. So q is the charge of the nucleus, small q is the charge of alpha particle. Let's say take that. So now if you observe that there is a relationship between closest approach distance and mass asking, so we can write mass is inversely proportional to r naught, therefore r naught is inversely proportional to m. So this is the answer. So if you observe that option A, that is 1 by m is correct, that is r naught is inversely proportional to m, so that is 1 by m. Okay, right. So please remember that the distance of closest approach, based on that we derived. Okay students, I hope the fourth question you understood. Next, fifth question. Listen, fifth question. Okay. See that fifth question. Consider the third orbit of helium ion using non-relativistic approach. The speed of electrons in this orbit will be, so here the k value is given as 9 into 10 power 9, that constant, and then z value we know that is the 2 because it is the helium atom. Then as usual the Planck constant 6.6 into 10 power minus 34 joule second. So this question asked in 2015. Okay students, now they are asking in third orbit, in the helium atom, in third orbit electron speed asking. Okay. So first you know the general formula or general relation between that particular orbit and then the speed. So first you know that formula, then if you know that formula directly you can apply that particular for any atom. Okay, for that atom z value you should know, then that particular orbit they will given. So that z value, that n value, if you apply, immediately you can get the answer. Okay, so you should know that formula. That is very important case. So first I derive this formula. Okay, not only for derivation, you can recapitulate. Okay, so please listen. This question, the right side I derive that formula. Okay, this is not only for helium, this is common. Okay, whenever they are asking velocity, immediately you recapitulate this formula, then apply the value, then within a minute you can find the answer. So please listen. Velocity of, see that the velocity of electron in nth orbit. Okay, so actually that common formula, after simplified we can get 2.18 into 10 power 6 meter per second. That's all. Idha mattum na vechirunga. 2.18 into 10 power 6 meter per second. Okay, into z divided by n. Okay, எந்த ஆட்டம் சொல்லியிருக்கிறாங்களோ அதோட அட்டாமிக் நம்பர் போட்டுக்குங்க. எந்த ஆர்பிட்டில் வெலாசிட்டி கேட்குறாங்களோ, ஓகே, எந்த ஆர்பிட்டில் வெலாசிட்டி ஆஃப் எலக்ட்ரான்ஸ் கேட்குறாங்களோ அந்த ஆர்பிட் n வேல்யூ போட்டுக்குங்க, அவ்வளோதான். So we can get the answer. Okay, I can remember this derivation. Generally, you know the velocity of the electron. Okay, so the denominator la paakadinga. First see that numerator part, k z e squared. So you remember, okay, this is familiar only, no? K z e squared divide by h bar. Okay, so actually h bar value nh divided by 2 pi. Okay, so h bar is equal to nh whole divided by 2 pi. So 2 pi is moving numerator. Okay, so we can write, so 2 pi k z e squared whole divided by nh. Okay, so k value you know 1 by 4 by epsilon naught. So after apply we can get z e squared divided by 2 epsilon naught nh. Okay, idella naam vechukena it is somewhat too difficult, you know. Okay, right, so we can write that is Vn is equal to, if we simplify except z and n remaining all constant, we can get 2.18 into 10 power 6 meter per second z by n. That's all. So this is highly important formula after simplify. Okay, so immediately we can find, not only for helium, okay, for any atom it is possible, for any orbit. So we can find out, so for helium, so helium z value is equal to 2, you know, and then they are asking particularly for third orbit. So therefore formula Vn, so here third orbit, you know, so V3 is equal to 2.18 into 10 power 6, this is common, into z by n, z value 2, n value 3. That's all. So we can get answer. that is 1.46 into 10 power 6 meter per second. Okay, so only 2 steps we can get answer. So please remember this formula, highly important. Okay, right. Sometimes in some questions maybe third orbit velocity, they're asking the ratio of third orbit and sixth orbit velocity. So like that also is possible to question. Okay, so after find out different velocity, let's you find the ratio what they are asking according to that. Okay students, it's very easy. So please remember this formula, 2.18 into 10 power 6 meter per second into z by n. Okay, right. So question number 5 over. Next question number 6. See that question number 5, option A, let's check. Yes, 1.46 into 10 power 6 meters. Okay, right. See that the same question, one more way it is possible to find the velocity of electron. They mentioned that the third orbit. So in third orbit you should find the energy. Okay, so hc divided by E is equal to h mu. So lambda is not given, Okay, 13.6 divided by n squared. Okay, so based on that, in third orbit energy you should find that energy is equivalent to, that is half mv squared. Then after that let's you want to find v value. So but it is somewhat difficult. Okay, so first energy கண்டுபிடிக்கணும், அதுக்கப்புறம் kinetic energy ஓட compare பண்ணணும், then v value, then one more thing, you want to take root also. Okay, so that is difficult. So please remember this formula alone. Okay, right. Next, 6th question. Listen. See that two particles of masses m1 m2 moves with initial velocities u1 and u2. Okay, on collision, one of the particle get excited to higher level. After absorption energy epsilon, if the final velocity of the particles be v1 and v2. Okay, right. So that relations is asking, these questions asked in 2015. Okay, so generally it is like a elastic collision. Okay, so in that area, so please remember from 11th standard, then like a law of conservation of momentum, total momentum is equal to initial momentum is equal to total momentum before collision equal to total momentum after collision. Like that here also, conservation of energy. Okay, total energy before collision is equal to total energy after the collision. But if you focus in that after the collision, here what happens, somewhat absorption of energy also you should included in that after the collision level. So please listen. See that law of conservation of energy. So okay, we know from the law of conservation of energy, generally, just I mentioned here, general case, kinetic energy in initial case, that means before collision, is equal to kinetic energy, that is that after collision, generally I mentioned. So we can write that kinetic energy initial is equal to kinetic energy final plus some absorption energies happen here. Okay, so see that this red color I mentioned, so that is absorption of energy. Okay, therefore initial is equal to final energy included that is absorption energy. This is given in question. Therefore, if you compare that option, so I can write the final energy is equal to initial energy, that is initial kinetic energy minus epsilon. Okay, the same thing I can translate it as kinetic energy equation form. See that kinetic energy final equal to kinetic energy initial minus epsilon. So kinetic energy final, okay, final alone without absorption energy, you can write that is half mv1 squared plus half mv2 squared equal to next initial total. Okay, total initial energy, you know that is half mu1 squared plus half mu2 squared, the minus this epsilon. Okay students, very easy question. So this is given as option B, so please check that option B. See that, okay, I derived right side, they gave left side half mu1 squared plus half mu2 squared minus epsilon. So this is kinetic energy initial minus epsilon is equal to kinetic energy final, that is half mv1 squared plus half mv2 squared. This is in option B. Okay, right. So easy question. Okay. Next, question number 7. See that again the Barber series, Lyman series repeated. Okay, so please listen. In the spectrum of hydrogen, the ratio of longest wavelength in the Lyman series to longest wavelength in the Barber series. Okay. Okay. Listen students, you must focus the longest wavelength. Okay. Longest wavelength na இப்போ say for example Lyman series எடுத்துக்குவோம். Lyman series n1 value you know 1. Longest wavelength is very next level, that is longest wavelength, that only give the longest wavelength. So n2 value, okay, n2 value only give for longest wavelength for Lyman. Like that the Balmer, in the Balmer series n1 value you know that is 2. But very next level only give the longest wavelength, that is n2 value is equal to 3 for Barber series. Okay. Okay. They didn't mention long distance. Long distance is represent infinite. This is you know longest wavelength. Okay. So please remember that one more thing. Whenever that what is that energy level is increasing, energy also increasing. அப்போ தூரத்தில் இருக்கிறது எனர்ஜி அதிகம் இன்க்ரீஸ் ஆகும். ஸோ தட் இஸ் ஃப்ரீக்வன்சி இஸ் மோர், தட் வேவ்லென்த் இஸ் லெஸ். அப்போ தூர போக வேவ்லென்த் கம்மியாகும். ஓகே, வெரி க்ளோசஸ்ட் லெவல் ஒன்லி வேவ்லென்த் இஸ் லாங். ஸோ அக்கார்டிங் டு தட் ஐடியா, லிசன், ஃபர்ஸ்ட் ஒன் ஃபார் தட் Lyman series. Lyman series, you know, n1 is equal to 1. n2 very next level, that is n2 is this only longest wavelength, to give longest wavelength, so nt is equal to 2. So based on that directly I apply 1 by lambda n for Lyman. So 1 by 1 square, that is 1, 1 by 2 square, that is 4. So 1 minus 1/4, so we can write 3 by 4 r. So lambda l is equal to 4 by 3 r. Okay, right. Next for the Balmer series, Balmer series actual n1 value you know 2, then n2 value you know very next level, that is 3. The same idea we can write here 1 by 2 squared, 1 by 3 squared, so that is 1 by 4 minus 1 by 9. So if we simplify we can get that is a 5r divided by 36. So lambda b is equal to 36 divided by 5r, that's all. So now they are asking the ratio between the wavelength in the Lyman series to the Balmer series for longer wavelength. So we can write lambda L 4 by 3R, lambda B 36 divided by 5R. So I can write as reciprocally 5R divided by 36. So if you simplify 4, 36 here, the 9 time RR will be cancelled. So we can get 5 divided by 27. Very easy question. Okay. So within a minute it is possible to find. So question number 7 is over. Okay. Right. So please remember, long wavelength means very next level. Okay. Long distance, they mention long distance means, that is N2 is infinite. Okay. Right. Okay students, next question number 8. Okay. So actually it is the last question today. Question number 8. Listen. Hydrogen atom in ground state is excited by a monochromatic radiations of lambda. Wavelength is given, that is 975 Armstrong unit. So the number of spectral line in the resulting spectrum is emitted will be, okay students, wavelength is given, number of spectral line is asking. So let us imagine in this question one hydrogen atom in ground state, okay, at a particular wavelength, that is 975 Armstrong unit, it is a fall on the, it can hit on the hydrogen atom. So after that it is absorbed the energy from that light photon. So the hydrogen atom moves to excited state. அது எந்த எக்ஸைட்டட் ஸ்டேட்டுக்கு போச்சு நம்மளுக்கு தெரியாது. அந்த எக்ஸைட்டட் ஸ்டேட் கண்டுபிடிச்சா மட்டும்தான் it is possible to find number of spectral lines resulting spectrum. அப்போ அதிலிருந்து ஒரு ஸ்பெக்ட்ரம் வரும் இல்லையா, அதில் எவ்வளோ லைன் வரும்னு கண்டுபிடிக்க முடியும். Number of, okay, the number of spectral lines in the resulting spectrum. So now I know you get some idea. Listen. Please listen. See that actually they are asking number of spectral line. Number of spectral line formula, n is equal to n into n minus 1 divided by 2. Capital N is equal to small n, n into n minus 1 divided by 2. Here capital N is nothing but number of spectral line. Small n is nothing but that is the excited state level. Usually we mention, that is n2. Okay, that only here, that is excited state level. Okay, actually what asking in the question, what is given in the question? Okay, one hydrogen atom, now at present it is in the ground state. Ground state lo or hydrogen atom irukku. Now we can pass the wavelength on the hydrogen atom. So after that it is absorbed, this hydrogen atom absorbs the energy from this photon. Okay, then it is moved to the excited state. Now we don't know that excited state. Okay, right. So here let us imagine already different state level at that particular energy. Okay, from the Bohr atom model you studied, So for first level, so please remember this is already we known value. So n1 value, that is minus 13.6 electron volt in the first orbit energy value of the electron, minus 13.6 electron volt. This formula, that is minus 13.6 divided by n squared into z squared. Okay, from that formula n1 is equal to minus 13.6 electron volt. Like that, if n is equal to 2, that is a second orbit, minus 3.4 electron volt. N is equal to 3 minus 1.51 electron volt. Then n is equal to 4, minus 0.85 electron volt. Like that it is going. Okay, so please remember this idea. Okay, right. So N1 is no is used, so we know already minus 13.6 electron volt, that is here. But excited state, whether it is 2, 3, 4, 5, anything, we don't know. So that level only we must calculate. Okay. Appa the calculate pandita, it is possible to find the number of spectral lines. Okay, right. So let's we calculate that the n value. Right. So we have only the clue. Lambda value, that incident lambda value is given, that is lambda is equal to 975 Armstrong unit. Then you must calculate the energy. Okay, right. So energy formula, you know, that is E is equal to hc divided by lambda. So everything known value, Planck constant, speed of light, lambda value is given. If you substitute, we can get 0.0205 into 10 power minus 16 joule. This is in joule. But if you observe that all the energy level in electron volt, I mentioned here electron volt. So if you divide by 1.16 10 power minus 19, it is entire value converted into electron volt. That electron volt value I got nearly 12.75 electron volt. Okay, actually 12.8 will come. Okay, so I can get it is nearest value for our convenient, I take that is a 12.75 electron volt. Okay, so please listen. So we know that energy different. Okay, this is the energy difference value between the two level. That is, you know, E is equal to the higher level energy minus lower level energy. E value, what we found E value now? 12.75 now. Okay, actually this is derived from this given data, we can get 12.75. Actually, what is this meaning? This is the energy difference between higher level minus lower level. Okay, let us imagine lower level already, you know, that is minus 13.6. Okay, then higher level we can calculate. See that? Okay, let us imagine that the difference between, if the difference between the fourth level, okay, minus 0.85 minus of minus 13.6, that is plus 13.6. So if you add this two, we can get that is 12.75. That is minus 0.85 plus 13.6, we can get 12.75. So absolutely the higher level now we can find it minus 0.85. So minus 0.85, that is equal to the fourth level. That excited state is fourth level. So that means what? Here this is N1, this is what? This is the fourth level, because this level only, that energy gap level, that is energy difference value, we can get it 12.75. So this is the fourth level. This energy value is minus 0.85. Okay, so now we can find n value is equal to 4. So immediately you know the formula, number of spectral lines, that is n is equal to small n into n minus 1 divided by 2. So n means, you know, excited state level. What is the excited state level? Now we can find n is equal to 4. So just to apply 4 into 4 minus 1 divided by 2. Okay, so if you simplify here 2 into 3, that is 6. So now we can find number of spectral line is 6. So from the fourth level, so that number of spectral lines emitted in that situation, you know, that is 6. Okay, so this is sixth, there is option number C. Okay students, please observe the concept. They are asking number of spectral lines, formula n into n minus 1 divided by 2. If you want to n, okay, so alternate way you should follow. You should find the corresponding energy. That corresponding energy you should compare with the already known value. So easily we can find the n value, then directly substitute here. Okay, so I hope today it's 8 questions we discussed. From that 8 question, maybe this question only it's take little time. Okay, remaining all the questions it is possible to find within half minutes or 1 minute. Okay, students, today discussion is over. Okay, so we will send that worksheet, so please complete, and if you have any doubt ask me. Okay students, thank you so much. Then the next class, the day after tomorrow, okay, we'll discuss that nuclear chapter. Okay. Thank you. Thank you, Arshia. Only 3 members in the line. Zeenab